Know that users set inaccurate time limits for their jobs, making scheduling optimizations ineffective and waiting longer in job queues. Hello everyone, me and my teammates Francesca will introduce you to the project we developed in our SOHPC adventure. Supercomputers are a very important tool for performing the calculation needed in the development of scientific studies. Some of jobs that are accelerated using supercomputers are completed quickly, and some can continue for months. The workload manager provides the most efficient and fastest distribution of the jobs to the nodes of supercomputers based on the time limit set by users. There are various optimizations to run jobs efficiently. The optimization we focus on in our study is backfilling optimization. Unlike the standard first-in, first-out scheduling, backfilling allows jobs to be completed earlier by distributing short-term jobs on idle nodes of supercomputers. However, some people can declare the limit times of their jobs much longer than elapsed time, which makes the scheduling optimizations ineffective. Our project proposed a solution to this problem using machine learning and various mathematical approaches. Machine learning is a good starting point when it comes to determine time limits rather than users. Lots of data are required to train a good machine learning model. The dataset consists of the past batch jobs of HARTREE-Center's supercomputer. As a result of analysis, we have seen that similar jobs generally run for similar elapsed time. For this reason, we thought that grouping similar jobs names will make it easier to guess when jobs that were not in the dataset before. Levenstein distance or edit distance, one of the famous methods in natural language processing, was used when grouping job names. Levenstein distance determines how many edits, insertion, deletion or substitution are required to convert one word to another. When estimating the time limit of jobs, prediction should not be less than the elapsed time. In case of underestimation, people's day of work can be wasted. Our aim here is to create a model that estimates the elapsed time of the jobs according to the job name and determines the time limit with a certain safety margin. Various regression methods were used and the highest performance were obtained with the gradient boosting, random forest and Huber regression model, but there were still a lot of underestimations. The weak point of this model was that it could not predict anything outside the regression line. As the second method to reduce the number of underestimation, I developed a regression model that I can determine characteristics of it manually. In manual regressor, data are grouped by job names. To avoid underestimation, the maximum elapsed time of each job names are selected, and predictions are made above a certain margin of safety from the maximum time. In addition, the manual regressor chooses not to predict the jobs that are elapsed at a certain rate close to the time limit. It also chooses not to predict the jobs that are less than a certain frequency. The weak point of this model was that it could not predict a job that elapsed more than the maximum time in past jobs. Despite all the adjustments made, some jobs were still unpredictable. To avoid this, these jobs have been blacklisted. In this way, with a one-time causality, these unpredictable jobs are considered while making predictions.
So while the previous model is powerful because it stores all of the user's information and history, it would require retraining often. So to avoid difficulties because of this, we take what we've learned from this model and apply it to a less expensive one.
So far, we have seen that previous job runtime and job name are great predictors for what the current runtime will be. Now, through testing and research, we find that storing the last 3 previous jobs is enough instead of the whole history. Now, we limit the history to 3 previous jobs because users tend to submit their job in batches. So storing too much information in the past would add noise, while storing too few would lose information on the variance. Based on the data we have, we also constructed new features where features can simply be seen as characteristics that describe our data and users. Some of the most important features include time passed between submission of 2 jobs, the number of completed jobs, and requested nodes within the cluster. The max, mean, and standard deviation are also very important to help us predict the runtime more accurately. Once we have our features, we can train and test our model using machine learning algorithms. Given that our data is time dependent, we can cross-validate by training on increasingly larger ordered subsets of the data and testing on the fixed size subsequent sets, as can be seen in the graphs. The average of all these tests will give us a true view on the performance of our model's prediction on runtimes. Next, we build a classification model based on the results of our regression model. From our previous test, we garner about 90% accuracy, where accuracy means that predicted runtimes are above what will be the actual runtimes and not underpredicted. In our model, we have the absolute requirement to avoid underpredictions without exception. So the classification model serves to identify those 10% of jobs that are underpredicted and classify them as bad jobs, where the 90% accurately predicted jobs are good jobs. Once identified, we can simply avoid estimating the runtimes of these bad jobs to avoid underprediction. When training our model, the key here is to downsample good jobs in order to predict bad jobs more accurately. Given our dataset, we have 2 categories with a 1:9 ratio. While this is a correct representation of our dataset, it is heavily skewed. As such, we perform downsampling and we create a balanced dataset. This may seem biased, but it works, and it allows us to identify all bad jobs without exception. This, of course, comes with the cost of misclassifying good jobs. This is a method heavily used in medical fields, where you cannot tolerate missing the identification of someone who is sick, even at the cost of misclassifying someone who is healthy.
Alright, so putting everything together, we have built two models to determine whether a user's job can be estimated safely and without underpredictions. The user can then get feedback from our algorithm suggesting a decreased, more appropriate time limit. By thus reducing the reserved time on the nodes, the cluster will be able to more efficiently schedule jobs. Thank you for watching.